All right, so our problem, should we choose to accept it? Actually, I'm going to start PowerPoint because that's going to make our lives a little bit easier. So I know that you guys love statics a lot. Probably your favorite class after programming, of course. So we're going to start with a smaller statics problem. Oh, actually, that makes life easier. Just grab the whiteboard. So the problem that I'm looking at looks something like this. Got some wall. Attached to that wall, have a couple pulleys, because what's a statics problem without a pulley? Yeah, you know? Let's see. Got a rope here. What's statics? Let's call it. If I have a statics problem without pulleys and rope, what are you doing with your life, right? And on that rope, got some weights. This guy down here, mass of 40 kilograms. That is a 4. Guy over here, mass of 30 kilos. Cool. I'm going to say that this angle is 30 degrees. This angle we do not know. Cool. All right. So for the purposes of this problem, let's say we're trying to figure out the mass of that guy. Cool beans? All right. Is that how I want to approach this? Because we got that, we know that. Yes, we want to do. Oh, actually, do I want to twist it like that? Hang on. I'm going to change it a little bit. Okay, never mind. So that's defined like that. Yeah, cool. Okay, so that's the problem. So I'm going to write that down somewhere because I'm going to have to get rid of the screen at some point in life. And we all know that happiness is a good free body diagram, or something like that. All right, we all got it? Almost. All right, so if this is just a statics problem, how would I solve for this guy? Well, how would I start into this? Okay, so I want to figure out all the weights of these guys. Good. And then what? What's the first step of any statics problem? Put it that way. Okay, I mean that's the answer to every statics problem. Well, it's either some of the forces is zero, some of the moments is zero, or you can't push a rope. Those are always the answers. But the first thing that you always draw in a statics problem is the free body diagram. Thank you. I'd say if that has not been beaten into your head yet, it needs to be. So we need to pick a spot and draw a free body diagram. I've kind of said that this is one, but it's not really what we want, right? Because there are like these pulley things going on, so the ropes are turning corners and stuff. I want a very straightforward, simple free body diagram that has a few vectors in it that are straight lines, and I can do trig on it, right? So let's do free body diagram where all these forces come together there, right? Let's just clear everything. So, all right, so I have that point where everything comes together. I'd say that's like the knot. I had a force going up this way. It's at an angle of 30 degrees to the vertical, so it's 60 degrees to the horizontal. Call that like theta left. Call this my tension going to the left. Call that my tension from my middle weight. This is my tension from my right set of weights. And that's my unknown angle. So that's kind of the system that I started off with. And then I've made a free body diagram of that point there. You all agree with that? Cool. So what's T mid? Cool. And that is? Say again? 392 newtons. Great. Okay. What's TL? It's the tension in that's the tension in this rope. Right? What's TL? Okay, and that was what, like 30 kilograms times 9.8? Yeah. Sorry, could you say the weight again, please? 294. 294 newtons. Great. Thank you. Great. And we know that that is true, even though the rope goes around the pulley because it's all the same rope, right? Rope has to hold, rope has to hold up the weight of that stack of weights. So that means the entire rope has to hold up that, because there's no sudden decrease in tension on it unless I grab it. I'm not. So we know what that is. Great. So now we have to solve for TRT or T right and theta right. Erase some stuff over here, make some more room. All right. So how do I do this? Bet you didn't know that you're having statics picks today, twice. So what do I do here? I have, yep. So define some positive directions. Say up and to the right is positive. So some of the forces in the y direction, what do I get? Okay. Or negative. I'm gonna use variables for a second here. So negative t mid. It's a little bit timid. That's a 6, I promise. Two the TO times. I believe that you're correct. I think we just missed our terminology. Yeah, that one. Cool. What else? Okay. Sweet. Positive or negative? Okay. Anything else? Great. So that equals 0, right? Okay. Let me move some stuff around here so I get a little bit more room out of this. All right. All right. So we got that. We can solve that for TRT, right? If only I had a TRK or TRICK, so that I could have trick and treat. Anyhow. So it gets like T mid minus TL sine theta divided by sine theta right. It's something like that. That should be left, left. For consistency's sake. Great. And we know that we're not there yet because we don't know what theta RT is, right? So what's next? Sweet. Okay, some forces in the x direction. Gets us what? Okay, of what? Is that positive or negative? Per our convention? Yep. And then? Awesome. Cool. That's 0. So we can solve that puppy out. Get something that looks like theta RT is the arc cosine of TL cos theta left, bless you, for TRT. Something like that, right? Except it's going to be problematic because TRT has sine theta RT in it, right? So we have to hold back a step and figure that out. So I'm going to substitute in TRT, or tension to the right. So I get can I erase this guy in the bottom right? Cool. Okay, got that, and I know that if I move TL cos theta L over, what's that? Cosine over sines, just 1 over tangent, right? So it's like a so it's like cotangent. Or I can multiply by the reciprocal and get something that looks like right? Something like that. So if I just take the arc tangent of everything on the left, I'll get my angle theta RT. Great. All right. So this is where we jump from this free body diagram into the code, because I've defined my problem in terms of variables, and I mean variables are what code's built from. So I'm all set. I just have to write these into a script. For reference, so I'm going to try to get both equations out here. See if I can just rewrite them quick. I made a mess. Okay, so I have an equation for theta RT. So that is the arc tangent, or the inverse tangent of T mid minus TL sine theta L, or TL cosine theta L. Great. And what was the expression that we had for TRT? We got that one written down. That? Cool. All right, so those are our two equations that are going to answer our question. So let's play the game. Pull up Python. All right. I'm just going to start a new file. Say this is statics pulley. Say this is to solve for the weight and chord angle in a basic statics problem. Exactly, if I wanted to reference it, it's 3.5 in Hibbler's study pack. All right, so let's see if I can pull that back up and save it into a thing. Sweet, it's still there. All right, so I got these. So I got these equations. I want to code things in some way such that I can such I can figure out the answers for both theta RT and TRT. First thing as I go to do that though is what am I going to need to need to build this code around, which is a kind of weird question, but the first thing I can see is, well, I have trig functions, so like atan, I have cosine. I might need to bring in like numpy to handle those. So that's one thing to think of. The other thing is I have inputs, right? I know what T mid is. I know what T left is. I know what theta left is. So I'm going to have some user inputs that I'm going to want to structure in here. So let's start out with that. Let's pull in numpy because we know we'll probably need it somewhere along the line, and then let's put some inputs down. So how do I pull numpy in? Okay, do it as NP because I like doing things in shorthand. Then what? What should I do next? Okay, tell me what to list. Okay, and what do we want to do with that? V92 what? Cool. And actually the input for that, if we go back to the problem, was mass, right? So we almost want to say, I'm sorry, getting ahead of myself. We almost want to say that the input is really in kilograms, and then we can compute the weight of it later. So this is what, 40 kilos? Cool. This way too, if we start with a purely round number, the code can keep track of all the decimal places, so we don't have to worry about rounding error, unless you care about rounding error at the 15th decimal place, at which point I think you need some help. But besides the point. So how do I compute the actual amount of tension based on that mass? Right, and I like being obnoxious about my decimals. All right, so we should probably title this something. And I should make sure that this is on the screen share. Great. All right. Okay, that's T mid. What else do we got? Which is? That's 30 kilos, right? Okay. And then we can get that tension the same way. Okay, what else do we got? Okay, that is. Okay, well, how do we treat it in the math? Which one? Also true. But the important question for our code here is that if if these are the equations that we're throwing in, what did we define theta L to be? I mean, did you pick 30 degrees and measured from the vertical, or 60 degrees and measured from the horizontal? If memory serves, this guy was derived. Whoopsie, that was a terrible red line. That was the worst red line of my entire life. This guy was derived from the summation of forces in the y direction, and TRT times sine theta RT. That would be a that would have got me a y component. So I see also a sine theta L here. Theta L must have been from the horizontal to the chord. So it must have been the 60 degrees. All right, so this must be 60. All right. So now we should, in theory, just have to punch those equations in and call it a day. Question is, I don't know what arctangent is. So let's go exploring. Make sure I'm sharing this. Okay, so what I'm going to type in is just numpy atan, because that's, I assume that it's in the numpy package, and I want the arctangent function. So if I go into the numpy manual, hey, I can type in it's saying you can type in numpy.arctan, or for us np.arctan, because we imported numpy as np. And it'll give me the inverse, and give me the inverse tangent. Awesome. Well, that's easy. So how do I use it? And this looks really frickin' confusing, right? Like really frickin' confusing. There's a whole lot of options here for something that should be relatively straightforward. So here's the thing with this. It has a whole bunch of confusing things there. If you just slip down over here, though, it'll have a couple of examples. So this is an example of using the arctangent function for on an array. You see these square brackets there. It computes the arctangent of each thing in the array. So if you can do it on multiple things, you can do it on one thing, right? At least you should. So I'm going to grab np.arctan. I'm going to run over here. I'm going to save all that work that I just did. I'm going to pull out my Python console. So this is the guy in the bottom right of Spider. I type import numpy as np. Then I'm going to say, let's see. Well, the arctangent of what? 1 should be what? 45? Because y and x would be the same length. So I'm going to say np arctan 1. I get that. What the heck? What do I do with that? Is that right? Is it weird? Why is it 0.785? You should see 45 degrees, right? Yeah. So if I need to take 0.785 times 180 divided by pi, I get 45 degrees. So what that's saying is that the output of this, of the arctangent function, is going to be in radians. So that's something that I'm going to have to keep in mind. But other than that, I should be able to use this as is, and just put everything that I want to inside of that. While we're here, well, should have like a in here it even says it too. It'll come out between negative pi over 2 and pi over 2. So you know, so you know that it's going to be in radians. Well, I'm going to while I'm here, I'm just going to look up, hey, probably have sine and cosine. So let's check out these. Same big things as same np dot sine is your sine function. Parameters x, it's the angle in radians. So this is something else that we're going to have to keep in mind. I can't just put 60 degrees and it has to be whatever the radian equivalent is. So I have one more stop in my code before I can start really crunching numbers. So pop back into here. So theta left, I'm going to want to convert that. And p dot pi is pi to a whole bunch of decimal places. I'll make sure that I always put this in the right units. All right. So I should just be able to crank out my thing now, my answer. So what do I type in? Yep. So tell me what to write. Okay. So if I look at my, let me just check the, so there's my equation there, right? So it's theta right equals arctangent of the quantity theta at t mid minus TL sine left, sine theta left, all that divided by TL times cosine theta left. So that's what I need to write. That's what I need to write in. However, my question's about as practical as it is pedagogical, because I can't have this up at the same time. So if someone has that written down, if you want to just say what it is so I can type it in, that'd be great. So what should I be writing in here? Yep. Then what? Yep. And it's np dot sine. Okay, and don't forget your parenthesis as you go through. And then I think we still have one open because this isn't closing everything. There we go, we got our arctangent in. That's in radians. All right, next thing be what? Yep. So how do we get that? Wasn't divided by something too? Okay, there we go. And let's just print those guys off. And I'm going to print it off to 4 decimal places. We'll stop moving. All right, I'm just going to, oh my goodness. I'm just going to print those 2 things out to 4 decimal places each. So this theta right, that's still in radians, right? So probably want to display that in degrees because everything else, my problems in degrees. So how do I get that to degrees? Yep. So, oops. Over here and just say times p dot pi over 180. Except it's 180 over pi, sorry. All right, so try to run that. Well, that's not very nice. It's also not very informative. I'm not sure if you guys are getting this there. This might just be how mine is. Yeah, I think what happens for me, yeah, if you look at mine, I did not close my parenthesis here. There you go. The only not good thing with this is that I didn't put units in. Tisk. So there we go. Sweet. And now if I wanted to change anything in this problem, I can do it without any problem whatsoever, which is super, super nice. How do I say this? Yeah. So that makes sense. Cool. So this is kind of the start of the wonderful world of modeling. You urge call where instead of cranking through a single kind of problem, eight different ways, you can set it all up in code once and just change a couple of local variables as you go. If you wanted it to be really exciting, you could have it read all your inputs from a text file. If you had like 4 problems, you could set up 4 lines of inputs, or have them read all in and try and just crank out 4 different sets of answers. So it's a tool. You can use it. If you saw the code that we just did is pretty straightforward. Like this is easier than most of the stuff you guys have done in the past month. So if this is entirely something that I think is within your grasp to be able to do. And I think honestly, you should have a look at doing stuff like that, like this, because it'll make your life a heck of a lot easier, especially when you have a particular kind of problem or something like that. That you just have to tweak a little bit. It'll be more interesting, honestly, more for your upper level classes. Especially when you start talking about design work, if you can test out, say, how a well, this is a good example. If you can test out an expression here and make a little calculator for a problem, be it for how much fluid you need to throw into a borehole, or how thick a bar needs to be in order to take a particular load. You can build this into a larger program that lets you design things. And that's kind of the coup de grace of coding. Where are you? So that's like this guy. There's what's called, the idea of this code was that it could run through a few thousand different ways to design a plane. So you have a whole bunch of different inputs to it. You have a whole bunch of different outputs from it, and you can smush all those individual calculators together into a fairly large code made up of these smaller guys in order to do it. Makes your life a heck of a lot easier to do when you can make your code do it all for you. Just saying. Well, that's that. Cool. All right. So if there are no questions there, let's look at the projectile motion problem one more time, and we'll call it a day. Let's move over to this guy. All right. Okay, so this problem, whiteboard, get rid of this stuff. Oh boy. I need, oh my, that's not good. There we are. All right, so for the projectile motion problem, we had ground, had ball being thrown, hit somewhere over here. We have some initial velocity and some firing angle. Question is, what's the highest height? And overall range of this projectile. And we know that we can compute those both directly, as long as you know the initial speed and firing angle. We have those equations, or we can make them up ourselves. You can definitely do this using time. I'm just lazy, so I am computing it directly. something like that. So in order to find each of those, I just have to run those two equations, and I'm done. I can also do this with time, and that's totally fine as well. It actually gives you a little bit more flexibility, because in these two expressions that I've written up, it assumes that there's no air resistance, there's no drag. As soon as you throw drag in there, these puppies are wrong, and you have to account for the thing's motion in time. So we're going to talk about that probably on Friday, but I'm not going to worry about that right now. Okay, so I have these two equations. Want to find max height, max range, but I don't just want to find it for. I don't want to just say it's the maximum height for a particular angle. The problems that we've been saying we've been looking at have been saying, I'm going to vary theta. I'm going to make it go between some minimum angle to some maximum angle. Suddenly this isn't the maximum height, suddenly this isn't the max range, it's just the height at one angle and the range at one angle. My question is, out of all those angles, what angle gives me the best height? Out of all those angles, what angle gives me the best range? That's my driving question now. So with that, it means I'm going to have to run these equations once for every angle and figure that out. So let's get to work. So I have some initial velocity, say 20 meters per second. Some starting angle, like the lowest firing angle that I'm going to look at. Let's call it 15 degrees for kicks and giggles. The highest angle that I'll look at let's call it 80 degrees. And in theory, that should be enough in information to solve the entire problem. All right. So I could step through all my angles, just one degree at a time, but I mean, I might miss something. I could call, especially when you make this a little bit more complex. I don't know what the actual result is. If I step through from 15 degrees to 80 to 80 degrees in steps of 1 degree, I could be off by up to half a degree, right? So let's step from our starting angle to our ending angle in steps of 0.01 degrees, 1/100th of a degree. So if I'm doing this, so I can say for I in range number of steps, and then say something like if I want to do something like that, because that'll get me whatever angle that I want based on where I start from and how many steps I've taken from there. For example, if I've taken 0 steps, so if it's my first time through the loop, I is 0, I've not stepped anywhere, theta starts out as my starting angle, right? If it's called in theory, if I've taken the total number of steps that I should, theta should be my ending angle, right? Cool. The question is, how do I figure out that guy? How do I figure out the number of steps that I need to take? Sweet. Okay, so number of steps equals end angle minus start angle. Okay, so that gives me, for this particular number, it gives me 65. But my steps are 0.01 degrees. So is that my actual number of steps? There we go. And then if we want to include our beginning or end, we have to add 1. Great. All right, so that gets us this is that. This gives us our angle in degrees. We know that everything's in radians, so theta equals theta times pi over 180. We need to import pi then. Okay, so now we got our angle in radians. All right, now what? Probably should compute the height and range. I did. Okay. Oh, sorry. You're about to say that? Okay, go for it. Mm-hmm. Yep. 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 So you can definitely do that. You can also just use these guys directly. Up to you. So I'm just going to use those directly because they're there. So H max. I'm going to call it a local max because that is only the max height for this particular launch angle. It's the maximum height achieved by this particular launch angle and this particular initial velocity. So H max local is going to be V naught squared times sine theta. So that sine theta is also squared. I'm just going to add some parenthesis around it. And then all that is divided by 2 times g. I could put in 9.807, but leaving it as a variable is better because I also just have 9.807s floating around. If I see a g, it's immediately obvious what that is. If I see like a 98.07 somewhere, I'm not sure if it's a typo or it's another number. So variables are quite handy. So I got that. Do the same thing for range. Go leave myself a comment. And if I was just looking at a single firing angle and a single initial velocity, I'd be done. But I'm not. I'm looking at a variety of them. So I want to find the overall maximum height and the overall maximum range. So where to from here? One way to do it is ask, have I seen a height this high before or a range this far before? That's one way to think about it. So before I get into this loop, the maximum height that I've computed is what? Nothing, right? Same thing with range. The overall maximum height and the overall maximum range is 0 before I get into the loop, because I haven't computed anything yet. So one way of computing whether or not this is the maximum height and this is the maximum range is to just ask, have I seen anything go this high before? So I can ask, is this greater than whatever overall maximum height that I presently have computed? And if it is, great. Similarly, speaking of typos, that should be our max, not our man. I probably want to keep track of what angles these occurred at. So I'll make up storage variables for those guys. And then I'll print all those out. Cool. So I just take whatever those maximums are after the loop's over, and I just dump it to the console. I just put in little curly brackets to insert those variables at different points in my string. So I'm saying max range is curly bracket, open close curly bracket meters at an angle of open close curly bracket degrees. The first variable in my format statement goes into the first set of curly brackets. Second variable goes into the second set of curly brackets. Same thing with the second one. Cool beans. So I should be able to say Python projectile motion. Ooh, that's not good. That's not good. What does that mean? When it's on line 17, 2, so it says float cannot be interpreted as integer. What's that sound like? Float cannot be interpreted as integer. It is. And it's saying that this guy should be an integer, expected an integer, but it's a float. Whether or not, like I can print out that variable. I bet you it's a whole number. See, it's 6,501. It is a whole number. It is an integer mathematically. But what's the difference between an int and a float in Python? What's the difference between an integer and a float in Python? Yeah, floats have decimals and integers do not. Because this has a decimal point, because it's a float, Python says it's not an integer. So we have to force it to be an an integer. So how can we force it to be an integer? Yep. So let's go back up here where I compute it, and I will make it an int. There we go. That's almost helpful, except something doesn't look quite right here. I mean, somehow I don't think that my maximum range is at 0.785 degrees. Yep. So come down to the bottom. Actually, I'll just change it in here. Because I don't use this for math. It's just for display. Okay. That looks better. Our ending angle was 80 degrees. So it makes sense that that is where the maximum height is. If it was at 90, if we went to 90 degrees, I expect the maximum height to be at 90. And then our maximum range is at 45 degrees, which matches up with what we'd expect as well. So this looks good to me. Perfect. Now, if I wanted to read stuff in from a file, like was in all of our homework problems, essentially just be replacing these first three things with whatever the starting angle, initial velocity, and ending angle were from that. So that's makes sense. Sound good? Okay, great. All right. So I know that you guys don't have homework presently assigned. Get some on Friday. Don't worry. I know that you're very anxious about getting homework. But did want to ask, have you guys had a chance to look at the final project at all? Okay. How's it's called? Do you guys have any questions about the math on that? I know we kind of did like a whirlwind tour of it once. Would it help to go through it twice? Okay. I saw at least one head nod. So let's bounce through that one more time. Oops, not that one. Okay. So that, back over to here. Need to grade stuff. Promise I'm going to grade stuff soon. I'm sorry. Let's see. Plugin, blah, blah, blah. Plotting final project. All right. So, coming back to this guy. So, the upshot of the project is that you have the ideal gas, gas law. That guy. You want to compute some compressibility factor Z. That's pretty much the entire project, to compute that one value, right? Trick is that in order to do that, it gets complicated. So you do it for some combination of gas. We're going to talk about that in a minute here. So you compute Z using this equation. It has a bunch of constants. A1s through A11. And you got all those values. So those are straightforward. But the things that you don't have values for, this TPR thing, and this row PR thing, would show up multiple times throughout it. So you have to compute those. It's kind of your next step. Okay, great. So how do you do that? So first thing's TPR. So TPR is this guy, T over T crib mixture. So T is just the temperature of the mixture. So you have some mixture of gases, and it's being heated to some temperature. That's like an input. But you also need to know the critical temperature of the mixture itself. That one's not an input. It's because you have some combination of gases. No one has written down what the critical temperature for an arbitrary combination of hydrocarbons is. So you have to compute that. So the method for that guy, oopsie, something like this. So here, let me pull up the whiteboard again. Here we go. So see if I can be cool. Apparently not. There you go. All right, so the inputs to this program are going to be the amounts of each gas. So all of the components were listed on the first page of the report. I'm going to abbreviate it here just for example. So, oh, come on. Why are you not letting me do what I need to do? There we go. So say that I have, dang it. Methane, ethane, and propane. Let's say those are my three gases, right? Oh, we're going to have one more. It's also going to have hydrogen sulfide and CO2. So the way that I express how much of each gas that I have is by its mole fraction. Mole fraction gamma is essentially what percentage of the mixture that it takes up. Okay. So for methane, you can say that's like 32%. Ethane, I can say that's 14%. Propane, I can say that it's 25%. I'm just making these numbers up as I go along. I'm going to say that's 24, just to make my math a little bit easier. 24 plus 32, that's 38, 40, 50, okay. Say it's a quarter of that and a quarter of that. Okay, so all of those should add up to 1. Right? Cool. And then I should also know what the properties of those are. So I should know and I can look up the critical temperatures and the critical pressures for each of these gases. I can look those up and come back with some value. I'm making these up for ethane. Say it's 1,000 Kelvin. Well, say 1,000 degrees Rankine. Ethane say it's like 800 degrees Rankine. Propane, it's like 725. I'm not sure. I'm just making this up. And say it's like 800 PSI, 725 PSI, 600 PSI for the critical pressures. So I'd find the critical pressure of a mixture of methane, ethane, and propane. And if you're looking back over here at equation 5, I can only use this for the hydrocarbons in the mixture. So I'll have some hydrogen sulfide and carbon dioxide. I can't use equation 5 for those. So I'm going to start off by, oh, come on, by just finding the critical temperature and critical pressure for these guys. And I'll call that my T crit mix, my P crit mix. So I can do that. I'm just going to erase these guys down here so I have a little bit more room. By multiplying the amount of the mixture that is occupied by that guy by the critical temperature or critical pressure of that particular component. So T crit mix would be mole fraction methane times the critical temperature of methane. It's going to be way too long, so I'm going to start abbreviating. Then add to that critical temperature of ethane times mole fraction of ethane. Mole fraction of propane times the critical temperature of propane. You on board with that? Hopefully we're not on board with the number of hydrogens, because I don't think I'm necessarily right. Yeah, it's 6. And then 1, 2, 3, 4, 5, 6, 7, 8. That's actually 8. Okay, now for the project, you would have all the other hydrocarbon components too. So you'd have butane, pentane, hexane, heptane, octane, nonane, whatever, right? Cool. So you'd add all those up, and that would get, and that gives you the result of equation 5. This guy here that it won't let me draw on. That's annoying. So that gets you equation 5. This guy here. However, we're not done quite yet. And that gets you equation 5 and also the critical pressure for the mixture. However, you're also going to have to correct that for your non-hydrocarbons, which is your carbon dioxide and your hydrogen sulfide. So you're going to have to correct those numbers that you just computed, and that's what equations 9, 10, and 11 are about. So the critical temperature of the mixture that you just computed, you find the value of E, which is equation 9, that corresponds to the amount to the mole fraction of carbon dioxide and hydrogen sulfide in your mixture. Subtract that off of T crit mixture. That gives you your actual critical temperature. And you can use that to compute your actual critical pressure. You on board with that? Cool. All right. So you guys are about to run out. So I'm just going to finish it up. You can check it online later. But cheers. Yep. Cool. One other thing to so that's how to correct it. One other thing to note before you go to before you plug T-curt mix into this, in addition to doing this with all of your hydrocarbon components, you also need to make sure that you do it for your C7 plus components. These are all your higher order hydrocarbons. So you have some mole fraction of those, but you won't have a T crit for those. You won't be able to look it up. What you're going to have to do is compute it. So jumping back over to here, that's what equation 6 and 7 are about. So given some mole fraction, or some molar mass of your C7 plus components, which is an input, as well as some specific gravity, you can compute a boiling point. Based on that boiling point, you can compute a critical pressure and a critical temperature for those C7 plus components. Once you have those, you can just plug them right into this equation. Plug them into this equation here with everything else. Then you take that, you drop down and correct it for your non-hydrocarbon components, and you're all set to go. Cool beans. So you correct it, you get a T-crit mixture corrected, a P-crit mixture corrected. You take those, you go back up to your original equation, go, hey, here are these, what you call it, rather go up to this guy, say, well, I have a temperature and a pressure of this gas. I can divide by my critical temperature or my critical pressure. I get this TPR or PPR value. And I can plug that into here and get my value for Z. Note that PPR is a component of this rho PR thing. All right. The only trick is that rho PR has a Z in it. That's fine. You just have to guess at what the value of Z is at first, and then let a fixed point iteration kind of method figure it out. So same as what you've been doing for your numerical method stuff. Any questions on that? All right, cool. Well, that's the bulk of the work there. Oopsie. Gonna come back over into here. That's why you don't like touch screens. The last bit of the project is to reproduce this graph. So you essentially just pick, instead of computing, you just pick a pseudo-reduced pressure, a PPR. You don't bother doing all that math for it. You just pick one. Pick 0.5, pick 0.7, pick 1, pick 1.25, pick 1.5, blah, blah, blah. You just pick one. And you pick a pseudo-reduced temperature. That's what these guys are. These TRs are. Those are pseudo-reduced temperatures. That's just T divided by T crit. PPR, that's P divided by P crit, right? So for this graph, you just pick values for each of those. Some of them are already listed here if you want to use them. And you compute a whole bunch of values of Z
It's kind of like when you had in your a pellet problem, you had to compute the radius of the pellet at different times, t. Here you're picking two variables instead of just one and computing the value of z at a whole bunch of different combinations of them. That's all that's going on here. So I'm picking a pseudo-reduced temperature, a T over T crit of 3, and then I vary my P over P crit from 0 to 15 and just pick a whole bunch of values off of, just compute a whole bunch of values of Z and graph them. That's all this is asking for. Sound good? All right, any questions? All right, the rest of the time is yours.